Davidson, speaking to us about gravitational waves.
Hi. Last summer, there was a landmark detection of gravitational waves by an experiment called BICEP-2 at the South Pole. Now, it's since been disproved, but the study of gravitational waves continues. We study gravitational waves because they give us a lens all the way back to the Big Bang. As you can see, they come from just teeny tiny amounts after the Big Bang occurred, and our best lens to looking at information at that era of the universe is gravitational waves. Now, gravitational waves come in a number of flavors and sizes, energies and wavelengths, just like light, but our ability to detect them nowadays is kind of small. There are a lot of experiments going on Earth, but they're all dealing with extremely high uncertainty and really hard types of gravitational waves to measure. As the universe expanded, the same amount of energy in a gravitational wave expanded as well, and they spread out and lost energy and became hard to detect. The way in which we detect them now is due to their imprint on something called the cosmic microwave background, which you can see here occurred at 380,000 years after the Big Bang. Gravitational waves left something called B-mode polarization on that cosmic microwave background. Now, the cosmic microwave background is just light that we see from space. And the B-mode polarization that we would see in this cosmic microwave background is just sort of a swirling pattern. So the experiment, BICEP-2 included, attempted to detect this swirling pattern and turn it into something called a power spectrum. Power spectrum tells you how much each wavelength of gravitational wave and each energy of gravitational wave shows up in the results we're seeing from the sky. Now, my thesis centered on imposing a limitation very early on in the gravitational waves to see the effect they would have on the later polarization of the cosmic microwave background. So I started with something very simple. What if one of the gravitational energies or gravitational wavelengths was 0? What if it just wasn't there? Well, the universe has changed a lot as we've come through the different eras. Different energies and different types of matter have become more and less prevalent. Now, that has a big effect on how the gravitational waves can travel through the different eras. Suffice it to say, everything I'm saying to you now in words can be said in the language of differential geometry and differential equations. But we took that limitation, 0 is 0, and brought it all the way forward with the gravitational waves to how it affected the cosmic microwave background at 380,000 years after the Big Bang. Now, the results we found was that this would introduce a very noticeable effect into any power spectrum that we saw today. 0 is 0 means that any wavelength that wasn't there remains not there, and this would be a huge peak or a huge spike in an otherwise smooth power spectrum. Now, this is a very noticeable feature that hopefully an experiment like BICEP-2 or the people that disprove them would notice going forward in the study of gravitational wave research, and I hope to limit anything that they might find. Thank you very much.